Section 7.2, inverse transforms and derivatives. So, like I mentioned at the beginning of 7.1, the idea is you take a dE, right? You Laplace transform it, and then you get an algebraic equation, and then you solve it, and then you inverse Laplace transform to get to the solution to the dE. Right? So we covered in section 7.1 the Laplace transform, right? In this section, we're going to cover inverse Laplace transforms. Okay, so that means given some function of s, can we find a little f of t such that capital F is the Laplace transform of little f? Right, which means f of t is the inverse Laplace transform of big F. Right, so before we saw that the Laplace transform of 1 is 1 over s, and the Laplace transform of e to the negative 3t is 1 over s plus 3, which means the inverse Laplace transform of 1 over s is 1, and the inverse Laplace transform of 1 over s plus 3 is e to the minus 3t. Let's look at the inverse Laplace transform of 1 over s to the sixth. So we know that we can get an s to the sixth in the denominator if we transform t to the fifth. Right? If we look back up in 7.1, right, the Laplace transform of t to the n is n factorial over s to the n plus 1. Right, so if we Laplace transform t to the fifth, we get 5 factorial over s to the sixth. Right? So if we want to inverse Laplace transform 1 over s to the sixth, we can almost do it if we had this 5 factorial, right? So we're going to start with Laplace inverse of 1 over s to the sixth, and we're going to compensate for the 5 factorial by multiplying and dividing by it, right? L inverse is also linear, right? We can pull this 5 factorial in and leave this one outside, right? So we're going to pull the numerator 5 factorial in, leave the other one outside, and now this is this, right? This inside is exactly this, which means the inverse Laplace transform of 5 factorial over s to the sixth is t to the fifth, right? And you can leave 5 factorial as a factorial, or you can expand it out to be 120. It doesn't matter. So the inverse Laplace transform of 1 over s to the sixth is 1 over 120 t to the fifth. And again, the important step here was we know a Laplace transform that looks close to this, but the constant's wrong. We can fix the constant, though. Right? We can fix the constant. Here's another one. Laplace inverse of 1 over s squared plus 7. Since we can't add s's out front, right, this is illegal. Adding functions of s is not okay. Constants is okay. You can add constants on the outside. Since we can't add an s, it must be a sine Laplace transform, right? If we look back up at our little table, right, the Laplace transform of sine is a constant over s squared plus number squared. We know that the Laplace transform of sine root 7t is root 7 over s squared plus, this is supposed to be square root of 7 all squared, right? Which means if I just compensate up here for this root 7, I can get to this inverse Laplace transform, right? So what am I going to do? I'm going to add a root 7, square root of 7 over square root of 7, right? Bring this one inside, leave this one outside, and I get the inverse Laplace transform of 1 over s squared plus 7 is 1 over root 7 stays, and then this becomes sine. Pardon me. Okay. Number 4. Laplace inverse of negative 2s plus 6 over s squared plus 4. We can split this over the addition in the numerator. And L inverse is still linear, right? So if I split this over addition, I can split the outside over the addition too. Right? Linearity says I can split this over addition. Excuse me. Okay. Negative 2s over s squared plus 4 plus Laplace inverse of 6 over s squared plus 4, right? This looks like a cosine because it's got s over s squared plus something. This looks like a sine because it's got number over s squared plus something. Right? If I just move this 2 out front, this is already cosine 2t, right? And if I move this 6 off, well, I need to add a 2, right? I need to add a 2 on top and bottom to get this to be sine of 2t, right? That's where this 1/2 comes from. This 1/2 comes from compensating by multiplying by 2 over 2. Right, multiply and divide by 2. So you can take this to be sine 2t. And that's it. That's it. Okay. Unfortunately, this only works, right? This is only nice if you have single terms in the denominator, right? This is like a single indecomposable term. You can't really factor this, right? However, sometimes you can factor the denominator. So this is a complicated one, right? And it seems like we need to split this up over the denominator. And that's a job for partial fractional decomposition, right? So how do we do partial fractions? Well, we start with s squared plus 6s plus 9 over all 3 terms. And then we want that to be some constant over s minus 1 plus some constant over s minus 2 plus another constant over s plus 4, right? So each one of these will become a separate denominator. Okay? And then we're going to multiply through by this denominator, right? Multiply both sides by this. So that's going to cancel the s plus 1 here and leave us with an s minus 2 and an s plus 4, right? And then on this term, it'll cancel the s minus 2 and we'll be left with an s minus 1 and an s plus 4, right? And that's what happens in the next step. And then you just pick convenient numbers, right? And what that means is you pick a number that's going to make a bunch of these terms go to 0, right? So s equals 1 is a good number to pick. Because if you pick s equals 1, then this term goes to 0 and this term goes to 0. So we get 1 plus 7 plus 9 is 16. Sorry, 1 plus 6 plus 9 is 16. And that equals a. This becomes 1 minus 2, which is negative 1. And this becomes 1 plus 4, which is 5. Right? And then solving this, you get a equals negative 16 over 5. And then you pick the other convenient numbers, which are 2, right? S equals 2, and then s equals negative 4 is the third convenient number. And then once you have those, right, we have this decomposition now, right? We have a, b, and c. So we've decomposed this fraction into 3 separate fractions. And each of these can be Laplace transformed pretty easily. So using the decomposition we just found, right? A times 1 over s minus 1, b times 1 over s minus 2, c times 1 over s plus 4, right? Now this inverse Laplace transform, this is an exponential, right? This is some exponential. And the easiest way to see it is it's this number here, right? If it's s minus alpha, right, on the bottom, 1 over s minus alpha is the Laplace transform of e to the alpha t, right? That's in the table. So the constant stays out front. The inverse Laplace transform of 1 over s minus 1, this is e to the t, e to the 1t, technically. Same thing in the second one. This constant stays out front, and this becomes e to the 2t. And then last but not least, the constant stays out front, and this becomes e to the negative 4t, right? Because this is s minus negative 4 in the denominator. So that's basically as hard as it gets, right? And sometimes you'll have, sometimes we'll have quadratics that don't factor. In the denominator, right? And the only thing to worry about there, like, if this was like, if we had something over like s squared plus 4, right? Then on the top you would need like an as plus b. You'd need like a linear function on top. If you have an irreducible quadratic on bottom, you need an as plus b on top. Okay, transforms of derivatives. When you take the Laplace transform of f to the nth power, right, you have to know the value of the derivatives at 0, basically. Excuse me. So if I take the Laplace transform of the nth derivative of f, I get s to the n, Laplace transform of f minus, and then the s's start counting down, and the values of f at 0 start counting up in derivatives. Right, so these are powers of s, right? And the last one's an s to the 0. And then these are derivatives, right? The 0th derivative, the first derivative to the n minus first derivative. We'll see some examples of this in a second. Okay, so here's how you solve an initial value problem. Right, you need these initial values. Right, need initial values. So the first step is you transform the differential equation using the Laplace transform. Right, so we're given a differential equation with some initial value conditions. We transform the equation with the Laplace transform. Then we're going to solve for the Laplace transformed variable y, which is Laplace transform of y of t. Once you have y, you're going to inverse Laplace transform that, and that will be the solution to the differential equation. Let's look at an example, right? dy dt plus 3y equals 12 sine 2t, given that y of 0 is 6. Okay, step 1, Laplace transform the whole equation. Laplace transform each of the pieces, right? Remember, constants can come out front. The constants can slide out front of the Laplace transform. Okay, we got the Laplace transform of the first derivative of y, Laplace transform of y, and the Laplace transform of sine 2t. By the theorem, the Laplace transform of the first derivative, right? If we look up here, Laplace transform of f prime of t. That's going to be s to the first Laplace transform of f minus, and then count down 1 power, you get s to the 0 f of 0, right? So the Laplace transform of dy dt is s Laplace transform of y minus y at 0. Right, so this is what goes here in the place of Laplace transform of the derivative of y. Okay. We also know that y of 0 equals 6, right? They told us that. This is why the initial values are so important. Okay. So we get the Laplace transform of y is capital Y. The Laplace transform of y is capital Y. The Laplace transform of sine 2t is 2 over s squared plus 4. And now this is an algebraic equation. Right? This is an algebraic equation in S. I can solve this for y, right? That's what I'm going to do. I'm going to solve this for y. I group up the y terms, right? So I get s plus 3 times y of s. I'm going to move the 6 across the equal sign, right? So this becomes 26 on top, and then the minus 6 becomes the plus 6. And now I'm going to divide both sides by s plus 3. Sorry, divide by s plus 3. S plus 3 down here. S plus 3 down here, right? Oftentimes it's best to, well, is it? Yeah, I think always it's best to combine these fractions on the right hand side, right? It's best to combine the fractions on the right hand side. So that's what happened here, right? That's where the 6 over s plus 4 squared came from, because I combined these two. So really this is like right, if you combine them. And then I divide both sides by y plus 3. S plus 3, excuse me. And then cleaning this up a little bit, we get s squared, 6s squared plus 50 over s plus 3 s squared plus 4. And now, since this is big Y, right, in order to get to little y, I just take the inverse Laplace transform of both sides. Right, inverse Laplace transform of this side gives me y. Inverse Laplace transform of this, I got to work on that. But thankfully I know partial fractions, right? And like I mentioned earlier, when the denominator is a quadratic that can't be factored, you need to use a linear function on top, right? So we get like a bs plus c instead of just a b. Okay. So partial fractions, multiply through by the denominator to clear out all the denominators. 6s squared plus 50 equals as squared plus 4 plus bs plus c s plus 3. Now, I've got 3 unknowns, right? 3 unknowns. And really, I've only got one convenient number. That's minus 3, right? There's no number that makes this 0. So I'm going to pick s equals minus 3 first. So I get 104 on the left-hand side. This becomes 13. This goes to 0, right? So I get a equals 8. Great, that's one down. Now, there are no other convenient numbers, so you just have to pick 2 numbers. It just so happens that picking s equals 0 is good, right? Picking s equals 0, this is usually a good option, because it'll make this right here, this bs, go to 0, right? So when you plug in s equals 0, you get this, which is useful. It's useful. We've already found what a is equal to, so this is not an unknown anymore, right? Plugging in 0 over here gives 50. A is 8. 0 plus 4 is 4. This goes to 0. C stays where it is, and 0 plus 3 is 3. So I get 50 equals 4 times 8 is, what is that? 4 times 8 is 42. I'm terrible at arithmetic. Plus 3c, right? Move that across. It's not 42, it's 32. Move this across. 15 minus 32 is 18. 18 equals 3c, c equals 6. Right? So now I know a and I know c. I just need to find b, and I'm just going to pick another number. Pick any number, right? S equals 1 works, right? 56 equals 8 times 5 plus b plus 6, 4. b plus 6 times 4. Solving it down gives b equals negative 2. I've now found a, b, and c, right? A, b, and c are now identified. So that means I have successfully partially I've run partial fractions on this left-hand side. So that means y of t is equal to the inverse Laplace transform of 8 over s plus 3 plus negative 2s plus 6 over s squared plus 4. And we've already found the inverse Laplace transform of 1 over s plus 3. That's e to the negative 3t. And we know this is a cosine beta t, and this is a sine beta t. I do need to add a 2 on top and bottom, right? I'm going to multiply by 2 over 2 out front and suck this 2 inside so that this becomes sine of 2t. And then I leave the 2 out front, right? So this means my solution to my dE, solution to IVP, right, is this function y. So that's kind of the power of, the Laplace transform, right? You can take a differential equation, which is hard to solve possibly, right? This is linear, so it's not impossible to solve, but it's annoying. It's annoying, right? You can convert it to an algebraic equation in y, solve that for y, and then take inverse Laplace transforms to get to the solution. It's not easy, but it's easier, right? It's easier. Okay.